Okay, here I wanted to go over some application problems that are very common with exponential functions. But before you actually get into the applications, you need to be able to understand the formulas that have to be used with the different types of problems. So the first formula we're to look at is the population growth formula. So one version of the formula is this one, where we have that P of t is equal to P naught a raised to the t power. And what's important to know about it is what the different variables mean. So in this formula, P of t, so this first term right here, this first part, is the population size. In most questions, this part is what you are looking for, is the population size. That means the P naught, okay, is your initial population. It's your starting point. A is going to represent your growth rate, so how fast your population is increasing. And notice for the most part, your growth rate is going to be greater than 1 because we're looking at the positive values, not negative. And then T is going to represent your time. And most problems, your time is going to be given to you in years because we're talking about how many years it's going to take, or over the course of this many years, for a population to grow. Now obviously problems can be written a little bit differently, but for the most part, in general, we're talking about years. Now another type of exponential we have is called radioactive decay. So radioactive decay has a couple different parts to it. So first we have just the general formula for radioactive decay. And so here you can see that its formula is almost identical to my population growth formula. The only difference is radioactive decay uses the variables A instead of P. Okay, but the terms have very similar meanings, where A of t, so this first part here, is going to be the amount of substance, because when we're talking about decay, we're talking about a substance that is getting smaller and smaller and smaller, okay, because decay means just that. It means decrease or getting in smaller value. And so most of the time those would be chemical substances. Now the one that most of us are familiar with is talking about carbon-14 dating. Carbon-14 decay is down here on the bottom, and you can see that its formula is slightly different. Here we have A naught E, and then we've got this value here. Okay, so this is the formula that you would use if you had to find carbon-14 dating. Now that would be things for archaeological sites. If you needed to date, say, the age of bones that you found, or if you needed to date tree bark, archaeological finds, that kind of stuff uses carbon-14 dating because it's going to tell you essentially how old the object is. So its formula looks a little bit different. It uses the E term in order to calculate it. And notice it has a negative here. That's because when we're talking about carbon dating, obviously we are trying to go back in time to see when the object was around, and that's how you figure out how old it is. The other type of decay rate that we have that is fairly common is your half-life. So notice half-life is essentially whatever your amount of substance is. The half-life takes a half away essentially every year is what you're doing. So half-life is whatever substance you have, you're going to divide it in half, and you're going to see how long it takes for that to occur. We use half-life dating when we're talking about radioactive or nuclear type dating, because radioactive chemicals tend to have half-lives, and what we have to look at is how long it's going to take before, say, your chemical that you're working with or your chemical that was spilled is safe to be around. Okay, so that's what half-life does. It kind of tells you how long it might take for something to reach a point where it is safe to be around. Okay. Now in math, we generally just look at these formulas and apply them to our problems, but these formulas are active and they are used in real-world applications that are going to be similar to some of the examples we're going to walk through. Now the last type of exponential formulas that we may deal with are the compound interest formulas. So here we have our formula that's used when you are compounding a certain number of times per year, as well as your PERT formula, which is the formula used when you are compounding continuously throughout the year. And so these deal with the finance. Okay. So what we're essentially going to do is I wanted to walk through different types of examples that you can see that are going to use these different formulas in different ways, which will hopefully give you a better grasp or concept on using exponentials to solve problems. So the first one we're going to look at says a family releases a couple of pet rabbits into the wild, and upon being released, the rabbits begin to reproduce at an exponential rate, as shown in the formula below. After 2 years, how large is the rabbit population, where N stands for the initial rabbit population and M stands for the number of months? Okay, so here remember I said most of the time you're dealing with years, but sometimes you'll deal with something else. Well, in this case we are dealing with months. So what we are saying is that these rabbits are probably reproducing at a very quick rate. So the first thing we need to know is what my M value needs to be. Well, in the problem, we initially said that you have 2 years. So we need to convert this to months. And the biggest thing that we have to remember here is that you need to essentially recall that 12 months equals 1 year. So if 12 months equals a year and I have 2 years, then that means I have 24 months that I'm working with. Now the other piece that I had is I had that N stands for the initial population. So we were actually told what N is. So when we're looking at that N value in the beginning of the problem, we were told that we had a couple of rabbits. Well, we don't have to be crazy. A couple literally can mean 1 male, 1 female. So 2. Okay. So here I need to fill in my numbers. So P is 2e to the 0.5 times my 24. You're going to run that into your calculator. Okay, so if I pull mine over, we're going to do 2 times, we're going to hit the E button, I'm going to open a parentheses, and we're going to do 0.5 times 24, and then hit enter. And you can see we actually get a fairly large number. And that tells you that after 2 years you now have 325,509.58 rabbits, which is essentially close to 325,510 rabbits. Okay. So let's look at another one. So here, suppose that $10,000 is invested at an interest rate of 5.4% per year, compounded continuously. Well, compounded continuously is that PERT formula. So the first thing that we need to know is that we are using P e to the RT to find my A value. In using that, I need to know what is P, what is R, and then what was my T. So in this instance, my P is going to be the 10,000. My R is your rate, which is 5.4%. You need to convert that to a decimal. So to do that means divide by 100, so 0.054. And then my T value is found in the second part. So here we don't know what it is. And our problem says find the exponential function that describes the amount in the account after T years. So in other words, this one is your setup problem. We need to write the equation to use. So I have my A of T is equal to P, so 10,000, E to the R, 0.054, and then T, because T is the unknown quantity. Now, since T is the only variable left in this problem, we have written the problem correctly. Now in the second part, it's telling you that in this case my T is going to be 5, and it wants to know the balance after T is 5. So I have to use the equation from the part before down in this second part. So what's important to note about that is if you make a mistake up here with your equation, then when you evaluate it, you're going to have the wrong evaluation. So you need to make sure your setup was accurate based on what the question wanted. So here we're looking at A of 5. So I have 10,000 E to the 0.054 times 5. Again, we can pull in your calculator, and we're going to go ahead and plug this in. So we have 10,000 times, you're going to hit your E button, open a parentheses, 0.054 times 5, and close it. Hit enter, and there you go. My account has a total of $13,099.64. So when you're dealing with money, you want to make sure that you always round to the nearest cent. Okay? Alright, this one says that we have a lake stocked with 640 fish of a new variety. The size of the lake, the availability of food, and the number of other fish restrict the growth of that type in the lake to a limiting value of 3,040. The population of fish in the lake after time t in months is given by the function. So again, here we're talking about a very short period of time. So we're going to go ahead and put our time in months. And we want to know the population after 10 months. So I have to simply use the equation given and plug in what I've got. So here I'm looking at P of 10. So this is going to be my 3040 divided by 1 plus 3.75 e to the negative 0.32 times 10. So for this one in your calculator, I would make sure that I am starting from the bottom and kind of doing it step by step. So step by step says first I'm going to work with the e side. So I'm going to do 3.75 times, I'm going to hit my e button, open my parentheses, negative 0.32 times 10, close it, and I'm going to hit enter. Now, saving this in my calculator, I'm going to hit +1 and hit enter. So this is my whole denominator now. So in my calculator, that is my denominator value. So what I'm actually going to do is I'm going to keep this in my calculator's memory, and I'm going to type my numerator, 3040. I'm going to hit my division sign, and notice above my negative is the word answer. So to get to the blue writing, I have to hit this blue second button. So I'm going to hit second. Notice I get this little second sign up here. It tells you that I'm using the blue writing instead of the big buttons. And I'm going to come down and I'm going to hit my negative sign. So notice it writes in ANS. ANS stands for the previous answer that's been saved in your calculator. And now I'm going to hit enter. And so that is going to give me the answer to my problem. Okay? And so here we come out with 2636.92. And since it doesn't tell you how to round, you can leave it as the 0.92, or if you wanted to round up, you could round it to 26 and 37. But this is going to be population of fish. Okay. All right. So this one is talking about the half-life of radium is approximately 1600 years. So essentially what that tells you is that every 1600 years, whatever quantity of radium you had has been halved. So if you say started out with 5 units of radium, or say 5 tons of radium, then 1600 years later you would have 2.5. So you would have it. And then fast forward another 1600 years and you'd have another half. So you would do 2.5 divided by 2, which gives you 1.25. Fast forward another 1600 years and you'd be down to 0.625. Fast forward another 1600 years, and so on and so forth. And so it tells you the time of which that you are constantly having the amount of product that you started with. So the question says, determine A so that A of t equals A naught A to the t describes the amount of radium left after t years, where A naught is the amount of time at t equals 0. And here there's a note that's saying you want to consider using at least 6 decimal places. And the reason for that is because we have a couple things we have to do to actually find this. First, we need to remember that when we're dealing with half-life, we are dealing with a very special equation, which says we are talking about A of t divided by 2 being A naught A to the t. Okay? So that's kind of the half-life that we're working with. So we have to be able to set some things up. So first of all, we know the decay rate formula is AT equals A naught A to the t. First of all, we also know that if we input a 0 in there, A naught A to the 0 essentially gives you your A naught value. Okay? So at time 0 is your A naught value. Now the other thing that we were told is that the half-life is 1600. So I know that if I'm looking at 1600, I have my half-life equation, which would say that I have my A naught divided by 2. And this is also then going to equal the idea that A naught, A to the 1600, would be the decay side of the formula. Okay? So here I have to be able to solve. So essentially what I'm saying is if we divide the A naught piece out, because that doesn't matter, what we actually have is that 1/2 is equal to A to the 1600. So I need to solve for A. So A is going to be my 1/2 raised to the 1 over 1600, which is going to give me 0.999567. Okay. Now the second part says how much of a 1 gram sample of radium would remain after 100 years. So I'm looking at A of 100 is equal to, my A naught is going to be that 1 gram. So this is going to be my 1 times my little a value, which is what I just found, the 999,567. And then this is being raised to that 100 years. So again, you would input that in your calculator. So 0.999567 raised to the 100, and that is going to give you 0.958 grams. So in other words, after 100 years, you still have almost 1 gram of sample remaining. Now that should actually make a lot of sense, considering it takes 1600 years for you to get the half-life, or the half amount. Now the last part says how much of a 1 gram sample would remain after 1,000 years. So this is going to be the same thing. We're looking at A of 1,000 is equal to my 1 gram sample times 0.999567 raised to 1,000 years. So in this case, we would have 0.648 grams. Again, that should make sense considering way back in the beginning we told you that it takes 1600 years to reach its half-life. In other words, that says it takes 1600 years to reach 0.5 if you had 1 gram. So the fact that after 1,000 years we're at 6.48 means we still have another 600 years to go before we get to 0.5, which is its half-life time frame. Okay. Alright, in this one it says you have $3,500 that you want to invest into a simple savings account for 2.5 years, at which time you plan to choose the account and use the money as a down payment on a car. Close the account, sorry, and use the money for a down payment on the car. You're going to find a local bank offering an annual interest rate of 2.75 compounded monthly, and then another bank is offering 2.7, but it compounds daily. So the question wants to know which bank should you choose. So here I have two banks. I have Bank A, which has a rate of 2.75%, and it is compounding monthly, so compounding at 12. And then I have a Bank B, which has a rate at 2.7%, and it is compounding daily. So daily here I would use 365. You don't have to get fancy, and you don't have to take leap year or anything like that into consideration, because this is just a best guess. And so our closest would be roughly using 365. So you have to set your compound interest equation up twice. So that equation is going to be A of t equals P times 1 plus R over N raised to the NT. So we have to do this for Bank A, and we have to do this for Bank B. So here we can have our A for Bank A is going to be my $3,500 times 1 plus my rate, 0.0275 over 12 raised to the 12 times 2.5, or 2.5. So again, you'll use your calculator, and the smartest thing to do is to start from the inside out. So if I pull mine over here, so again, if we start from the inside out, we would start inside the parentheses. So I would start with 0.0275. I'm going to divide that by 12, and I'm going to hit enter. And then I'm going to plus 1 and hit enter. I'm going to raise it, open a parentheses, to the 12 times 2.5. Close it and hit enter. And then I need to multiply that by 3,500 and hit enter. And notice you get $3,748.79. So Bank A would give you $3,748.79. Okay. Now you need to set up Bank B. So my second one, so my Bank B is going to be 3,500 times 1 plus 0.027 divided by 365 raised to the 365 times 2.5. And we're going to look at what that comes out to be. Okay. So here, again, we can pull out our calculator. And again, we're going to work from the inside out. So we have 0.027 divided by 12, or sorry, divided by 365 and hit enter. We're going to plus 1 and hit enter. We're going to raise it, open a parentheses, to 365 times 2.5, close it and hit enter. And then we're going to multiply that by 3,500. And we get 3744.40. So here this one was 3744.40. So if we look at the two banks, even though the second bank is compounding every day, the first bank, or Bank A, is actually the better bank to bank at. And that comes from even the smallest amount of percentage is going to make a big difference in the long run. So here you would want to choose Bank A, or the bank that uses the 2.75% compounding monthly. Okay? Now the last type of problem that I wanted to look at is a population problem. So it says, it's a car problem. It's depreciation. And it says that depreciation is the decrease of an item's value and can be determined using a formula similar to your compound interest formula. And here V is the new value, and it says if the particular car you buy upon graduation from college costs $17,500 and depreciates at a rate of 16% per year, what will the value of the car be in 5 years when you pay it off? So what do we know? Well, we know P is going to be the cost of my car, so $17,500. I know R is going to be the rate, which was 16%, so as a decimal is 0.16. And then T in this case is going to be 5 years. So what's missing is we have to find V. So we need to plug it in. V is equal to $17,500 times 1 minus the rate, so 0.16, raised to the 5 years. So again, we would pull out your calculator and we would work inside the parentheses first. So here we have 1 minus 0.16 and hit enter. Then we're going to raise that to the 5th power and hit enter. And finally multiply that by 17,500 and hit enter. And so when we finally pay off the car is going to be valued at $7,318.71. So the value again is $7,318.71. So those are a small collection grouping of different exponential application problems that you may see or come across. If you have any questions, please let me know. Otherwise, I'll see you next time.